This train has no engine, no fuel, no turbines, no drive shafts, yet it reaches 603 kilometers per hour. So what is actually moving it? It is not inside the train. It is inside the track. This is how the fastest train on Earth actually works. Imagine soaring across continents at speeds that redefine travel, not on wings, but levitating inches above a track. At 603 kilometers per hour, Japan's SCMaglev holds the world record for the fastest train ever recorded. It travels without touching the track, floating approximately 100 millimeters above the Guideway. What if I told you the secret to these incredible Maglev trains isn't just advanced engineering, but a revolutionary blend of materials you've probably never even heard of? Get ready to discover the invisible superheroes. The carbon fiber laminates and ceramic matrix composites that are reshaping the future of high-speed ground travel. First, deep foundations are excavated and reinforced to support the elevated Guideway structure. Reinforced concrete pylons are cast to create rigid supports, capable of carrying high dynamic loads. Precast Guideway beams are manufactured with embedded steel reinforcement to ensure structural stiffness at 600 kilometers per hour. Each beam is aligned to millimeter level tolerance to prevent instability at high speed. Propulsion coils are embedded directly into the Guideway, transforming the track into a linear motor. Expansion joints are installed to allow controlled movement, as temperature changes affect the concrete structure. Carbon fiber prep-rig sheets are prepared in temperature-controlled storage to preserve resin integrity. Precision molds are prepared to define the aerodynamic geometry of the train body. Layers are stacked in alternating orientations to maximize strength and stiffness. The layered composite is vacuum sealed to remove air pockets before curing. High pressure and elevated temperature cure the resin to create a rigid composite structure. Ceramic matrix composites are processed at high temperature to achieve exceptional thermal resistance. The composite panels are integrated onto a lightweight structural frame to reduce overall mass. The completed composite shell provides high stiffness with minimal weight. Superconducting coils are precisely wound to generate extremely strong magnetic fields. The coils are encased in reinforced housings to withstand intense electromagnetic forces. Liquid helium cooling systems are integrated to reduce operating temperature to approximately minus 269 degrees Celsius. At this temperature, electrical resistance drops to nearly zero, allowing immense current to flow efficiently. The magnetic field strength is carefully calibrated to ensure stable levitation performance. At low speeds, the train rides on auxiliary wheels because magnetic lift is not yet sufficient. As speed increases beyond approximately 150 kilometers per hour, magnetic forces begin to generate measurable lift. Repulsive magnetic interaction between onboard superconducting coils and Guideway coils produces vertical lift. Once sufficient lift is achieved, the wheels retract and the train transitions to full magnetic levitation. The train stabilizes at a levitation gap of approximately 100 millimeters above the Guideway. Sidewall coils provide lateral magnetic guidance to maintain precise alignment at high speed. The Guideway contains long stator coils that function as the stationary part of a linear motor. Electrical current is supplied in sequence to create a moving magnetic field along the track. The moving magnetic field synchronizes with the onboard magnets to pull the train forward. Acceleration is controlled by adjusting the frequency of the electrical current supplied to the Guideway coils. At high speed, The synchronized magnetic wave continuously pulls the train forward without physical contact. Braking is achieved by reversing the magnetic phase, converting motion back into electrical energy. The elongated nose is engineered to reduce aerodynamic drag at speeds above 500 kilometers per hour. At extreme velocity, aerodynamic resistance becomes the dominant opposing force. When entering a tunnel at high speed, compressed air generates powerful pressure waves. These pressure waves travel through the tunnel and must be carefully managed to prevent structural stress. Aerodynamic shaping and magnetic guidance ensure stability, even under crosswind conditions. Structural reinforcement and damping systems prevent resonance at extreme speeds. Testing begins with controlled low-speed runs to verify system stability. Speed is increased incrementally to monitor levitation stability and propulsion synchronization. Sensors continuously measure magnetic gap, vibration levels, and structural stress. Tunnel performance is evaluated to ensure pressure waves remain within safe structural limits. During final validation, the train accelerates to 603 kilometers per hour under controlled test conditions. This sustained run establishes 603 kilometers per hour as the fastest train speed ever recorded. Through precision engineering and scientific discipline, Japan's SCMaglev redefines the limits of ground transportation. Unlike conventional trains, a maglev system does not contain a traditional engine. Instead, the motor is built directly into the guideway. A synchronized magnetic wave pulls the train forward without physical contact. In a maglev system, propulsion is infrastructure-driven rather than engine-driven. There are no rotating drive shafts or onboard traction motors inside the train. Propulsion power is distributed continuously along the entire guideway. High-voltage substations supply electrical energy directly to the guideway coils. A moving magnetic wave travels ahead of the train, pulling it forward. Motion is generated by the infrastructure, rather than machinery carried on board. In a maglev system, the track is the engine. From composite structure to superconducting magnets and infrastructure-driven propulsion, every system works together to achieve 603 kilometers per hour without an engine.